Alright, this video is over random variables. And first, I want to make sure you understand a random variable is really simple to understand. A random variable simply takes on a numerical value that describes the outcome of some chance process. So it does need to be a numerical value. And there are two different types of random variables. So as we learn about random variables, we're going to learn about each type. And the first type we're going to learn about, probably spend the most amount of time on, is what we call a discrete random variable, and I'll use RV to stand for random variable. Now, a discrete random variable means that the numerical value that this chance process could take on is a listable value. Okay, there is a discrete or a permanent set of values that could happen. So let's just give you an example. Let's just say that we toss 3 coins, and we're looking for how many heads could come up. How many heads. So when you toss 3 coins and you're looking for how many heads, this is a random variable because I don't know how many heads there's going to be, but I do know that there's going to be either 0 heads, 1 head, 2 head, or all 3 could be heads when I toss this coin. So we use a capital letter X to represent a random variable. So random variables are capital X. Capital X is kind of like the question, how many heads can there be? And there could be 0, 1, 2, or 3. And we use little x's to represent each individual outcome. So we could say one little x is 0, another little x is 1, and a third little x is 2, and a fourth little x is 3. You don't necessarily have to write those, but just understand that a little x is the individual outcome, and a big X is the overall idea of how many heads there's going to be. And now the other thing we're going to learn about is a probability model. Now, a probability model is simply a model, a chart, you could say, that simply shows what could happen and what the probability is. So usually right next to each outcome, we write the probability, and we define it like this. We put a capital X equals a little x, because what we're going to find is we're going to find the probability that the number is 0, and then we're going to find the probability that the number is 1. So keep in mind, capital X is the idea of how many heads there's going to be, and little x is each individual outcome. And the fact that it's called discrete means that there is a listable number of outcomes. I can actually list all of the different things that could happen. So all 3 being 0 is really, really easy. Or no heads, that's really, really simple. So that means we need all tails. So that would be 0.5 to the 3rd power, all tails, 0.5 to the 3rd power. Now the issue here is the probability of a tail and a head is the same thing, and that's okay. So we get 0.5 to the 3rd power is 0.125. So 0.125 is the chance of all tails, meaning no heads. I could also come down here and figure out the probability that I get 3 heads. That would be 0.5 to the 3rd as well. That would be head, head, head. We're up here, remember this would be tails, tails, tails. So again, since the probability is the same, it's also 0.5 to the 3rd, and of course that is again 0.125. Now, what about 1 head? Well, there's 3 different ways that can happen. I could have, let's see, I'm going to come over here and list the different ways. I could have the head first and then a tail and a tail. I could have a tail and then a head and then a tail. I could have a tail and then a tail and then a head. All of those is 0.5 to the 3rd. I mean, understand that the probability of each one of these happening is 0.5 for the head, 0.5 for the tail, 0.5 for the tail, 0.5 for the tail, 0.5 for the head, 0.5 for the tail. So all of them are 0.5 to the 3rd, but I have to understand that there's 3 different ways that can happen. So I'm going to put a 3 in front of this because I'm going to need to multiply the fact, but there's 3 different ways that can happen. It would be this way, which is 0.5 to the 3rd, or this way, which is 0.5 to the 3rd, or this way, which is 0.5 to the 3rd. So 3 times 0.5 to the 3rd is 0.375. So the probability of that is 0.375. And the next up, I need 2 heads. Well, 2 heads could look like this, head, head, and then tail, or it could be head, tail, head, or it could be tail, head, head. Those are the different options for how that could occur. And once again, that would be, each one of these is 0.5 cubed. But there are 3 different ways it can happen. So that's 3 times that, which is once again 0.375. So I have my probability of a 0. There's only one way that can happen, all tails. Or 3 heads would be all heads, or the different options in between. Now, one way to check and make sure that you have your probability model correct is that all the probabilities should add up to 1. And if I add up 0.125, 0.375, 0.375, 0.125, they do add up to a grand total of 1. So that's one way of showing that you do have a correct probability model. Let's look at a slightly different example here to help us understand. Here's a probability model, and this was done by the U.S. Census. They asked how many different languages do you speak? And there was 1, 2, 3, 4, 5 were the different options. That's a numerical outcome. It's listable. Nobody spoke 6. Nobody spoke 7. It was either 1, 2, 3, 4, 5. Everybody spoke a language. There was nobody that spoke 0. And one way I could check to make sure this is a legitimate probability model is I could simply add up 0.63 plus 0.295 plus 0.065 plus 0.008 plus 0.002, and of course they do add up to 1. So that's one way I could check that they all add up to a legitimate probability model. Now, a couple different things we can do with this. One is we can make a different type. This is a very basic probability model, options and probabilities, very simple. But I could also make like a histogram that kind of represents this as well. So I'm going to have a chart, and sorry for my very bad lines, but on my chart I have 1, I have 2, I have 3, I have 4, and I have 5. So again, these are the different options, and that's a really bad straight line. And for example, the vertical axis would be the actual probability. So 1, if I would go up to 63. So if this is 100% up here, and this would obviously be 50% here, the 1 would go up to 63%. So I don't know, maybe somewhere in this range. And that would show that the probability of one language being spoken is 63%. 2 would be around 29.5%. So I got to try to figure out where I think 29.5% would be. And I could get more specific with intervals here to help that make it look easier. 3 is really low. It's 6.5%. So that'd be somewhere way down here. 4 is 0.8%, so that might not even register as a line, and obviously my line's not very good here. Let me try to maybe make this a little bit neater, not much, but a little bit. Okay, so there's 4, which is very, very low, and then this is 5 languages is 0.2. I mean, that wouldn't really even register on this scale, but very, very low. So it's just a different way that you can use like a histogram to help explain your probabilities. Now, there's several questions I could ask. For example, I could say, what's the probability somebody speaks at least 3 languages? If I said, what's the probability somebody speaks at least 3 languages? That means they speak 3 or more, 3 or 4 or 5. And you hear that word or? So I'm going to add, it'd be 0.065 plus 0.008 plus 0.002. So the probability that somebody speaks at least 3 languages would just be adding those up, 0.065 plus 0.008 plus 0.002, and you would get 0.075. 0.075. So there is a 7.5% chance that somebody speaks at least 3 languages. I could also do something like, what's the probability somebody speaks at most 2 languages? At most 2 languages. Well, remember, at most means that's the highest. So it would be 2 or less. So this would be somebody speaks 2 or 1 language. So in this case, it'd be 0.295 or plus 0.630. And if you add up 0.63 plus 0.295, you get 0.925. So 0.925. So there's a 92.5% chance that somebody speaks at the very most 2 languages. So you see how you can answer several questions dealing with this probability model. Now, one thing, we're going to use the same example to explain this next topic. One thing we talk about probability models is what do we expect to happen? And to understand this, I want to go back to probability real quick. What does this mean, 63% of people speak 1 language? Well, it doesn't mean if I have 100 people, it means that there's going to be 63 exactly. It means the long run. We've talked about this in class, that probability is what happens in the long run, not 1 or 2 or 10 or even 100 trials, but what happens over the course of a very long amount of trials. We would expect 63% of people to speak 1 language. So what I want to ask is a kind of a similar question. I want to say, what's the average number of languages that a person speaks? Or what do I expect a person to speak? So what we're trying to find here is we're trying to find the average. I'm going to use mu for our average, right? We're trying to find the average number of languages somebody speaks. So remember, X is how many languages you speak, capital X, right? So mu is the average number of languages that somebody speaks. This is what I want to try to figure out. Another way that we could write this, another symbol we could use, is a capital E for expected. What's the expected number of languages that somebody speaks. So we can use either one of these notations, a mu meaning the average or E meaning expected. This is all the same thing. So when we're talking about this, we're talking about the mean or the expected value. So if you were to run across somebody on the street, how many languages would you expect them to speak? And to find this, it's actually very simple. So I'll show you the formula. The formula might look a little bit complicated, but it's a very, very easy formula. For the most part, it's very straightforward. What we do is we take each individual outcome. I'll use an I there for individual. Each individual possibility, so 1 or 2 or 3 or 4 or 5, and we multiply that by the probability for that individual outcome. And then what we do is we simply add up all of those ideas. So we take so in our example here, the average number of languages that we would expect is very simple. We just take 1 times its probability, 0.63, plus 2 times its probability, 0.295, plus 3 times its probability, 0.065, plus 4 times its probability, 0.008, and finally plus 5 times its probability, 0.002. Sorry. So again, you take each individual outcome times its probability, multiply, and then you add all of them together. So that's what that capital E here is. This is the summation. Be careful, because this is literally an E, capital E for expected. This one right here is the summation that we've known in math class. So when you do this, you get, if you use your calculator, you get 1.457 languages. Now it's important to understand what this value means. Obviously nobody could speak 1.457 languages. You speak 1, 2, 3, 4, 5, right? So this is the expected value in the long run. So let me explain this in 2 ways. Meaning that if I were to ask a ton of people, right? So I'm going to go randomly out of the grocery store and I'm going to ask people, how many languages do you speak? Most people are going to tell me one. And maybe somebody says 2, and then maybe there's another bunch of ones, and very rarely I might get a 3, and then a bunch of ones, and I ask somebody, and then somebody says 2, and then for the most part I am going to get ones, because again, that is most common, 63% chance, and I'm going to keep asking people, and very rarely I might get a 5 thrown in there, but again, that's going to be very, very rare. For the most part, I'm going to get a bunch of ones, and again, maybe a 2 thrown in there, but for the most part, that's what I'm going to be getting, right? So imagine I do this and I have tons and tons of data and I average that data out. I say, what's the average number of languages somebody speaks? In the long run, after many, many, many trials of asking many, many, many people, I would get 1.457 languages. So it's kind of like probability. It means that what do you expect in the long run? After asking many people, what do you expect the average number of languages to be? 1.457. So it's a very, very easy process to figure that out. Hopefully it's a very easy formula. You can easily do that by hand. It doesn't take too long to multiply and add. Now, let's do another example real quick here. I want to talk about a roulette wheel. We know, if you don't know, maybe you do or you don't, on a roulette wheel there are red spaces, there are black spaces, and there are green spaces. Okay, now on the roulette wheel there are 18 reds, 18 blacks, and there are 2 greens. So the 18 reds and the 18 blacks are numbers, and the 2 greens are 0 and 00. So all you need to know is red, black, or green. So let's just say I put my money on red. You know, I'm trying to win red, and I'm trying to think of what could happen. Okay, so I have $1. I put it on red. What could potentially happen? Well, this is where we create a probability model, right? So very basic probability model here. The first thing is I could win $1. That's what happens when you play the roulette wheel. If you put $1 on red and red comes up, you could win. And the probability that I win, here I'm creating my probability model. The probability I win that $1 is 18 out of 38. Again, 18, 18, and 2 is 38 total spaces on a roulette wheel. Now the other option is, of course, I lose negative. I lose my $1. I don't win, and that would be, of course, the 20 out of 38, the 20 out of 38 chance that I lose. So if I play this roulette wheel many, many times, I play and play and play, not just once, I play a long period of time, I keep betting one, sometimes I win, sometimes I lose, I keep betting $1 many, many times. What do I expect to win in the long run? What do I think my average winnings would be in the long run? What do I, wrong either, what do I expect to win in the long run? Remember, X is how much money I'm going to win. It's either going to be $1 or a loss of $1. So to figure this out, I just take my outcome, $1, and I times it by the probability, 18 over 38. And then I add this to my other outcome of -1 times its probability, which was 20 out of 38. And if you do this and you do the math correctly, you get approximately negative 5 cents. Negative 5 cents. If you multiply and add those together, negative 5 cents. And this is exactly why the casinos stay in business. They know that over the long run, over playing this game many, many, many times, not just 10 or 100 times, over the course of a long run, people expect to lose 5 cents. And that is why the casino stays in business. Because in the long run, over the course of a whole lot of plays, people will lose an average of 5 cents at the roulette wheel. Okay, let's before I actually go back to that problem, I want to go back to our language problem here. I want you to also understand that with an expectation, with an average, a mean, an expected value, also comes variance. Right? Everything varies, right? We would certainly expect some, over the course of a long run, somebody to speak 1.57 languages. Hopefully that makes sense. But that number also varies. So we want to find out that there is a standard deviation attached to this as well. And to explain this, I'm going to introduce a second problem, or a new problem here. So this, so we continue to look at new problems. Let's just say that I'm a car dealer and I sell cars, and on any given day I could sell 0 cars, 1 car, 2 cars, or 3 cars. Never going to sell 4 or more. This is a legitimate probability model because they do add up to 1. And I said, okay, well, over the course of, long time, days and days of selling cars, how many cars do I expect to sell? What is my expected value? What is my mean over the course of a long run? Well, hopefully by now this is very easy to calculate. So 0 times 0.3. Outcome times probability, plus 1 times 0.4, outcome times probability, plus 2 times 0.2, outcome times probability, plus 3 times 0.1, outcome times probability. So if I do this over the course of the long run, 0 times 0.3, I really don't need to do that because I know that's going to be 0, but do it anyway just to make sure you're following suit. 1 times 0.4 plus 2 times 0.2 plus 3 times 0.1, and I get 1.1. So over the course of the long run, over the course of many, many days of selling cars, I expect to sell an average of 1.1 cars in the long run. But the problem is that this number varies. How do I find how much it's going to vary by? And that is what we, you guys know this, we call it standard deviation. Now the formula, I'm going to write the formula down. First off, we use sigma for standard deviation. Sigma is the standard deviation of the expected value. We could also do standard deviation, SD, of the random variable, either one that you want to go with. To find this is a little bit different formula. Let me kind of walk you through what you need to do here. First, you need to take each individual value. So each individual outcome, we'll call that xi, right? Each individual outcome, 0, 1, 2, or 3. And then you need to subtract away the mean. You need to subtract away the average outcome. Because remember, standard deviation is a measurement of how far values are from the mean. And the problem is, if I do that, some are going to be negative, some are going to be positive, and I could potentially get a 0 or some values that are going to cancel each other out. So I need to square that, and this should sound a little bit familiar through our standard deviation formula. So I take each individual outcome minus its mean, square that, and then I need to times that by its probability, right? So I'm going to take each value minus its mean squared times by its probability. And what I'm going to do is I need to add all these up. So I need to sum all those up. So I got to do this for every single value. Okay, do this for all the values, and then I have to take a square root. Because I squared, I need a square root around all of that to get back to the standard deviation. So a little bit more of a confusing formula, but it's really not that difficult. You take your value minus its mean squared times it by its probability, divide it, or then add all those up, and then giant square root around all of that. So I'm going to start the process, and I'm going to take 0, that's my first option, minus the mean, 1.1, squared times its probability, times 0.3. Then I'm going to do this again. I'm going to do 1 minus 1.1 squared times its probability of 0.4, times the probability of 0.4, plus 2 minus the mean of 1.1 squared times its probability of 0.2, plus the next one, or the last one, is 3 minus its probability of 1.1 squared times its probability of 0.1. And I'm going to add all those up, and after I'm done adding all those up, I'm going to draw a giant, sorry for how bad it is, a giant square root around all of that. And again, it would take a little bit more time to plug that into your calculator, but it's not that hard. You just got to suck it up and do it. And you do get a standard deviation of the random variable for this particular problem to be 0.943. So here's the idea, and this should sound familiar to stuff we've already learned. Over the long run, I expect to sell 1.1 cars, but I know that that number might vary. Sometimes it might be a little higher, sometimes it might be a little bit lower, and it's going to vary by 0.943 cars. Okay, so this tells me, what does that mean? It means that any given day, I will typically be off from the mean by 0.43 cars. Remember, that's a random variable. How far off will you be from the mean? So typically speaking, on a given day, I'll be 0.943 cars away from the mean, which is 1.1, because I certainly expect 1.1 cars on any given day. So hopefully that's not too bad. It's a little bit of a complicated formula, but overall not too bad. All right, so the last thing I want to talk about now is continuous random variables. Continuous random variables are very different than discrete random variables. Continuous random variables, you can't list all outcomes. And because I can't list all the outcomes, it makes a probability model hard to do, because remember, probability model, you got to have all of your outcomes there with the probabilities attached. So continuous random variables, we can't list all the outcomes. So what we'd have to use, we have to use density functions, or we use density curves to describe a continuous random variable. And we've actually seen these in the past, believe it or not, and the most famous density curve that we've ever have, I hope everybody remembers, is the normal model. So let's just kind of give a quick example here. Let's say we're talking about 3-year-old females, so 3-year-old girls, right? So 3-year-old females, okay? And maybe doctors have let us know that the average weight of a 3-year-old girl is 30.7 pounds, and the standard deviation is 3.6 pounds. Now, first off, I want you to understand why this is considered continuous, because we cannot list all of the weights that a 3-year-old female can weigh. I mean, that weight, especially just even to 1 decimal, that list would be extremely long. 30.7, 30.8, 30.9, 40, 41.2, 42.3, 43.4. I mean, it's endless, the list. It's continuous, which is why I can't make a probability model. But what I can do is, if I'm told that it follows a normal model, right? A normal model is one of our density curves, one of the most famous density curves, then actually I can have a way to kind of explore this continuous random variable. I know that the normal model looks basically something like this, and I know that right smack dab in the middle is going to be the average of 30.7 pounds, and I know that I can go up 1, 2, 3 standard deviations, down 1, 2, 3 standard deviations. And what's a standard deviation? 3.6, so I can go up 3.6 pounds. So if I do so, that would be 30.7 plus 3.6. That puts me at 34.3, and I can go up another 3.6 pounds to be at 37.9. And sorry, my handwriting's kind of messy down here. And up another 3.6 to be at 41.5 pounds. And we all have talked about what this normal model means. It means that most data is going to be in the middle, near the mean, within 2 standard deviations. And it would be very rare for a child to be outside of 2 standard deviations, and extremely rare to be outside of 3 standard deviations. So again, I can ask a similar question. I can say, what's the probability? I'm going to actually use a capital P here. What's the probability that a girl weighs, let's say, at least 30 pounds? Okay, what's the probability that a girl that weighs at least 30 pounds? Now, we know that that means 30 pounds or more. So how do I figure this out? Well, I need to find the area that represents 30 pounds or more. Well, I have to figure out where 30 pounds falls. 30 pounds is actually going to fall somewhere down here, because I know that 1 standard deviation below puts me at 27.1 pounds. So 30 pounds falls somewhere right around here, right? I'm going to use a different color here so we can see this. So I need to figure out the area of 30 pounds or more. We've actually already done this, believe it or not. Remember, it comes down to z-scores. I have to figure out what this person's z-score is. So to find the z-score, I'm going to take 30 pounds minus the average of 30.7 divided by the standard deviation of 3.6. And when I do that, you could do this along with me. It's pretty easy. I get negative 0.1944. So her z-score here is negative 0.1944. And that makes sense. It's just a little bit below the mean, not even a full standard deviation below. And then what I can actually do is, remember, how do I find the area of this shade up here? Well, I'm going to have to use my calculator, right? Remember, normal CDF on our calculator. I'm going to tell it, so I'm going to tell it to start at negative 0.19. I'm going to tell it to start at negative 0.1944, and I'm going to ask it to find the area, or the probability in our case, to 99. So when I do that on my normal CDF on my calculator, I'm going to do negative 0.1944, comma 99, and I get 0.5771, which means that 57.71% of 3-year-old females weigh 30 pounds or more. And it's a continuous normal model. So again, I don't have an actual probability model to calculate this. Like we saw in the other examples with the cars and the languages I speak, because I could list those. Here it's continuous. I can't list them. So I have to use a density curve, and the most famous density curve is the normal model. I guess the issue that we'll talk about in class is what happens if it's not a normal model. Then you can't use z-scores. You can't use normal CDF, and it makes it very difficult to do. But most of the time, we will be saved by the normal model, and we'll talk about that more in class as well. So hopefully random variables make a lot of sense to you guys. We have discrete random variables and continuous random variables, and we also talk about our expected values of what do we expect to happen in the long run. And hopefully that is very, very easy, and that formula was very simple. But with an expectation, with an average comes a standard deviation, how much it may vary, and we had a formula for that as well. And if you need to go back to the video to review any of that or take any notes, feel free. But that is our unit on random variables.